In this video, we will discuss correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. For example, on page 469 in the book, Table 10-1 gives data on kilograms of chocolate eaten per person in 23 countries and the number of Nobel laureates per 10 million people in each of those countries. In the USA, we eat, on average, 5.3 kilograms of chocolate annually and have 10.8 Nobel laureates per 10 million people. It's always wise to explore sample data before applying a formal statistical procedure. We should use a scatter plot to explore the paired data of Table 10-1 visually. Here is that scatter plot. We can observe the following about the data set based on the scatter plot. There are no outliers, data points far from all the other points, and the points appear to show a pattern of increasing values of the Nobel rate corresponding to increasing values of the chocolate consumption rate. In the scatter plot above, we see a distinct linear pattern. We say that there is a positive linear correlation between x and y, since as the x value increases, the corresponding y values also increase. In the scatter plot above, we see a distinct linear pattern. We say that there is a negative linear correlation between x and y, since as the x values increase, the corresponding y values decrease. In the scatter plot above, we see no distinct pattern, which suggests that there is no correlation between x and y. In the scatter plot above, we see a distinct pattern suggesting a correlation between x and y, but the pattern is not that of a straight line. It looks more like a parabola. Because conclusions based on visual examinations of scatter plots are largely subjective, we need more objective measures. We use the linear correlation coefficient R, which is a number that measures the strength of the linear association between the two variables. The linear correlation coefficient R measures the strength of the linear correlation between the paired quantitative x values and y values in a sample. The linear correlation coefficient is sometimes referred to as the Pearson product moment correlation coefficient in honor of Carl Pearson, who originally developed it. Because the linear correlation coefficient R is calculated using sample data, it is a sample statistic used to measure the strength of the linear correlation between x and y. If we had every pair of x and y values from an entire population, it would instead be a population parameter represented by rho, the Greek letter rho. Key elements. In notation, we've got N is the number of pairs of sample data. This capital sigma denotes addition of the items indicated. So sigma x is the sum of all x values, and sigma x squared indicates that each x value should be squared and then those squares added. Whereas sigma x in parentheses quantity squared indicates that the x values should be added and the total then squared. So avoid confusing sigma x squared and sigma x quantity squared. Sigma xy indicates that each x value should be first multiplied by its corresponding y value. After obtaining all such products, find their sum. R is the linear correlation coefficient for sample data, and rho is the linear correlation coefficient for population data. Given any collection of sample paired quantitative data, the linear correlation coefficient R can always be computed, but the following requirements should be satisfied when using the sample paired data to make a conclusion about linear correlation in the corresponding population of paired data. First, the sample of paired data, the paired XY data is a simple random sample of quantitative data. Second, the visual examination of the scatter plot must confirm that the points approximate a straight line pattern. And third, because results can be strongly affected by the presence of outliers, any outliers must be removed if they are known to be errors. The effect of any other outlier should be considered by calculating R with and without the outliers included. Formulas. Two formulas are given. The first is a good format for calculations, while the second promotes understanding of the material. The first, R equals n times sigma xy minus sigma x times sigma y over the square root of n times sigma x squared minus sigma x quantity squared times the square root of n times sigma y squared minus sigma y quantity squared, or R equals sigma zx zy divided by n minus 1, where n denotes the z-score for an individual sample value x, and zy is the z-score for the corresponding sample value y. Round the linear correlation coefficient R to 3 decimal places so that its value can be directly compared to critical values in table A6 on page 692. Interpreting the linear correlation coefficient. Using p-value from technology to interpret R, we use the p-value and significance level alpha as follows. If the p-value is less than or equal to alpha, this supports the claim of a linear correlation. If the p-value is greater than alpha, it does not support the claim of a linear correlation. Using table A6 to interpret R. Consider critical values from table A6 or technology as being both positive and negative. Draw a graph demonstrated in future slides, and then use the following decision criteria. Correlation. If the computed linear correlation coefficient R lies in the left tail beyond the leftmost critical value, or if it lies in the right tail beyond the rightmost critical value, that is, absolute value of R is greater than or equal to the critical value, conclude that there is sufficient evidence to support the claim of a linear correlation. No correlation. If the computed linear correlation coefficient lies between the two critical values, that is, the absolute value of R is less than the critical value, conclude that there is not sufficient evidence to support the claim of a linear correlation. Warning. Remember, the methods of this section apply to a linear correlation. If you conclude that there does not appear to be a linear correlation, it is possible that there might be some other association that is not linear, as in the scatter plot below. Always generate a scatter plot to see relationships that might not be linear. Properties of the linear correlation coefficient. First, the value of R is always between -1 and 1 inclusive. That is, -1 is less than or equal to R is less than or equal to 1. Second, if all values of either variable are converted to a different scale, the value of R does not change. Third, the value of R is not affected by the choice of X or Y. Interchange all X and Y values and the value of R will not change. Fourth, R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. And fifth, R is very sensitive to outliers in the sense that a single outlier could dramatically affect its value. The following examples illustrate different methods for finding the value of the linear correlation coefficient R, but you need to use only one method. We are not demonstrating the use of technology here, as all the book shows us is a series of displays you will find if you find a variety of technology. Using technology is always a good option, but you will need to learn to use it for yourself, as we simply cannot cover all of the programs that you could make use of. If manual calculations are absolutely necessary, the first formula in slide 11 is recommended. If a better understanding of R is desired, the second formula in slide 11 is recommended. We will find the data of R for the data used in the table below, which takes 5 specific data points in our chocolate consumption Nobel laureates data set. I should have included a couple of big skips here, I guess, but I didn't, so this is what we've got. For our chocolate values, we have 5, 6, 4, 4, and 5, and for our Nobel values, we have 6, 9, 3, 2, and 11. Using the first formula from slide 11, the value of R is calculated as shown on this slide and the next. Here is the variable X. Here the variable X is used for the chocolate values, and the variable Y is used for the Nobel values, because there are 5 pairs of data, n equals 5. Other required values are calculated in the following table. So this gives us all of our values, the x squared, y squared, and xy products. And it tells us that the sum of x's, sigma x is 24, sigma y is 31, sigma x squared is 118, sigma y squared is 251, and sigma xy is 159. Using the first formula from slide 11 with the data from the second table in the previous slide, R is calculated as follows. And I'm not going to read all of this out. You can see for yourself what this does and duplicate it if you want to. R comes out to be 0.795. We will use the same data set as in the previous example with the, in this case, the second formula from slide 11. If manual calculations are absolutely necessary, the first formula from slide 11 is much easier than the second, but the second formula has an advantage of making it easier to understand how R works. As in the previous example, the variable x is used for the chocolate values, and the variable y is used for the Nobel values. In this formula, each sample value is replaced by its corresponding z-score. For example, using unrounded numbers, the chocolate values have a mean of x bar equals 4.8 and a standard deviation of Sx equals negative 0.836660. So the first chocolate value is converted to a z-score of 0.239046 as shown here. The table below lists the z-scores for all of the chocolate values and for all of the Nobel values. The last column of the table lists the products Zx times Zy. Using the table above, we calculate sigma Zx times Zy equals 3.179746. So the value of R is calculated by using the indicated formulas as shown below. R is again 0.795 approximately. We know from the preceding examples that the value of the linear correlation coefficient is R equals 0.795 for the 5 pairs of sample data in the table used. But if we use the 23 pairs of sample data in the original table, we get the following StatDisk results, including R equals 0.801. We now proceed to interpret the meaning of R equals 0.801 from the 23 pairs of chocolate Nobel data. And our goal in this section is to decide whether there appears to be a linear correlation between chocolate consumption and numbers of Nobel laureates. Using the criteria given in the key elements, we can base our interpretation on a p-value or critical value from table A6.